In this video, I'll go through the equations from chapter 7 on conservation of energy. So in the last chapter, chapter 6, we talked about work and kinetic energy. Now we're going to introduce the concepts of potential energy. And basically the deal is this: you will only be dealing with two types of potential energy. One will be gravitational potential energy due to the gravitational force. The other will be elastic potential energy due to a spring force. These two forces are both called conservative because it doesn't matter how you get from one height to another. When the force of gravity is acting, the amount of work you do is the same. So what that means is if you had, say, two heights, y1 and y2, whether you go straight up from y1, y2, or whether you kind of jiggle around and go like this, or whether you go past and come down, it doesn't matter. The amount of work you do to get from y1 to y2 against the force of gravity is the same. And so we call the force of gravity a conservative force. It's the same with a spring, a mass on a spring. If you're going to go from position 1 to position 2, it doesn't matter whether you just pull straight from 1 to 2, or you go past and you come back, or even if you do some weird thing. Well, you can't really do a weird thing going off this surface. You have to stay on this horizontal surface. And the work that you do against the spring is the same, no matter how you get from 1 to 2. And so those are called conservative forces. And when you have a conservative force, you can define a potential energy. Notice friction is definitely not a conservative force. So if we were moving a mass along a rough table, the amount of work we do totally depends on how we get from position 1 to position 2. So if we just go straight from 1 to 2, it's not nearly as much work as if we drag it past and bring it back, because you're losing heat the entire time this longer route. So friction is not conservative. So friction is, we call it non-conservative. Whereas these two guys, these are conservative. Okay, so as long as we have a conservative force, we can define potential energy. I like to use PE, but your textbook uses U. So U gravity is defined to be m times g times y. Okay, so this U stands for potential energy in joules, gravitational potential energy. M is mass in kilograms. So obviously it depends how much mass something has as you're moving it around. You're going to do a lot more work if it's heavy. G is not an acceleration, it is the strength of the gravitational field. It's 9.8 newtons per kilogram. Always a positive number. That is not the acceleration due to free fall. That is the strength of the gravitational field. And then Y is the vertical position in meters. And this all depends where you define 0. So if you have a floor and you have a table and you have a book on the table, if you let the floor be 0, then clearly the table is at some higher height, maybe 1 meter. But if you decide to make the table 0, then the floor is at -1 meter. It's below. So it's very, very important where you decide to make your 0. And you have to define that for every single question. Okay, so how does work relate to these potential energies? Well, the work done by gravity is equal to the negative change in potential energy. That is a definition for all potential energies. Work is always the negative change in potential energy. So this is negative mgy final. Dear, I don't know what's happening to my pen here. Final minus mgy initial. Now the formula sheet uses 2 and 1, but how do you know which is initial and final? It's very important that it's the negative change, and change is always final minus initial. Okay, so why is that and how does that work? Well, remember, this is the work done by gravity, not done by you. This is done by gravity, by the gravity force. So you're always doing the opposite. That often you're doing the opposite of what gravity is doing. So if we have heights and you have a mass, the force of gravity is always down. That never changes. So there's the force of gravity. Now, if you lift it up, so you lift, you're doing positive work because if it moves up, the displacement is up. Then you do positive work. So this is W work by you is positive. But gravity is working against you. It's doing negative work. So W by gravity is negative. Now the change in potential energy, obviously if you lift something up, you give it more potential energy. So the change in potential energy is positive. And so now you know why. See, that's a positive and this is a negative. That's why there's this negative in the formula here. So if you pull something up to do positive increase in potential energy, you're doing work, but gravity is doing negative work. It's doing it against you. So that's why there's this negative in there. And that's really important. Okay, now if we're doing conservation of energy, it is something that is always conserved. So it is a quantity that's always conserved. Now energy, it's just a bookkeeping device. It's just a number that we calculate. So if we only have gravity working, no other forces, then the conservation of energy looks like this. Well, the conservation of energy always looks like energy before equals energy after. And this after means after something's happened. It's fallen down, it's hit a spring, it's gone along a rough surface, something has happened to it, it's moved, almost always moves. So you add up all the energy before and you get the energy after. And this sum is just all the types of energy that it has. So far we know about kinetic, we know about gravitational potential, and in a second we're going to know about elastic potential. So if we only have gravity and kinetic energy to worry about, then this just looks like kinetic energy initial plus gravitational potential energy initial must equal kinetic energy final plus gravitational potential energy final. Okay, so that's when there are no other forces, only gravity is working. So this K, remember, is kinetic energy in joules. And I stands for initial and F stands for final. And then this is potential energy, also in joules. And so the problems that you're going to do that have to do with that are things like throwing a ball in the air. So gravity is the only force working, and the kinetic energy is going to go up and down depending on what happens to the gravitational potential energy. Or you may have a roller coaster. And there are lots of examples of that in the videos that you watch and the problems that you do. So as something goes along a roller coaster, the gravitational potential energy is defined by its height above zero. You always have to define zero. And if it's moving, it has kinetic energy. If it's above zero, it has potential energy. And you just go along and the numbers will always add up to the same thing. So up here, you may have that the gravitational potential energy is 100 and the kinetic is 0. And down here, if maybe the gravitational potential energy has dropped to, say, 40, well, then the kinetic's going to have to be 60 because they all have to add to 0. Down here, if the potential is dropped to 30, then you know the kinetic must be 70. And so the sum of these two numbers, no matter where you are, as long as only gravity is the thing acting, will always add to the same total. Okay, it's the same with a ball being thrown up in the air. So as the ball is going up and down. Doesn't matter how it's going up and down. Could be going at an angle, could be going straight up and down. But at every position, you simply add the two numbers, gravitational potential plus kinetic, and you're always going to get the same total. Okay. Now, if we introduce a spring into the situation, we have elastic potential energy. And that, by definition, is 1/2 kx squared. And if you remember from the last video, I derived the work done by a spring, and I got negative 1/2 kx squared. Well, sure enough, here it is again, that the elastic U potential energy is the negative of the work done. Notice how there's no negative here. So this is for spring potential energy. Could be a bungee cord, could just be a regular spring, mass on a spring. So what I mean by that is a spring like this. K, that's the spring constant. That's how the spring is. So K is a big number. It's a very taut spring, like on a trampoline or in your car. And the units for K are newtons per meter. That's a property of the spring. As long as you don't wreck the spring, go past its elastic limit, that remains constant. And then X is the position from equilibrium. So it all depends where it starts. And equilibrium is usually when it's just relaxed. And this is in meters. Now notice how in the equation we have an x squared. So it doesn't matter whether you stretch it. So x, say this is x equals 0, and you pull it along and you stretch it. The potential energy stored is the same as if you push and you compress it in this direction, because you take x and you square it. So whether x is positive or negative doesn't matter. Okay, so that's elastic potential energy. And so as a spring, we're going to see in the future chapters, when we start letting these masses oscillate by themselves on a spring, as this goes back and forth, the energy is swapping from kinetic to potential to kinetic to potential. So as you pull it aside, you're storing up potential energy. As it moves over, you let go, and that potential energy turns into kinetic energy as it goes zooming past equilibrium. And the sum, so if we only have a spring acting, then once again, conservation of energy says that the elastic potential energy initial plus the initial kinetic energy is going to be the elastic potential energy in the final position plus the final kinetic energy. And those two numbers will always add to the same value. We say that that's constant. Okay, so this is only if a spring. Okay, in other words, no gravity, no friction. No gravity and no friction. Okay, so problems with springs just going back and forth, that's the equation you want to use. Okay, now, if we have all these things going on at once, then you simply add them all up. So the total change in any type of energy is 0. So that's the next equation here. Now, I'm not sure what they mean by U int on your formula sheet, but basically what this can be, this could be non-conservative work. So plus heat, I just call it heat, is equal to a constant. The only kind of non-conservative work that you're going to deal with is the work done by friction, and that's always going to be heat, which is just force of friction times the displacement. And this is equal to heat. So this is the total change in kinetic energy. So whether something is slowing up, slowing down, or speeding up, that's the change in potential energy. And that could be elastic and gravity going on at the same time, like bungee jumping. You would have elastic and gravitational as you spring up and down. This is change in potential energy. and then the non-conservative. So this is considered non-conservative work. That's what your book calls it. I just like to call it heat. Now, the way I actually like to use this equation is a bookkeeping method. So what I do is I list the types of energy. So there's kinetic energy, there's gravitational potential energy, there's elastic potential energy, and there's heat. And then there's a total. And these quantities are put into a table. And then what you do is you go with the position. So it might be position A, position B, position C. So this may be, say you jump off a cliff, you're bungee jumping, you're going up and down, you're at different positions. You send something down a roller coaster, and as you roll along, you have different positions. So the deal is, if you know these quantities at any one position, so say we know we start at the top of a cliff, we're not moving, but we're way up there, so we have 120 joules of gravitational potential energy. We're bungee jumping, the bungee cord hasn't stretched at all, so there's no elastic, and we haven't lost any heat yet, so this is 0. When we add across this row, we see our total energy is 120 joules. Now that number is not going to change as we go up and down on this bungee. So let's say we're here, and we've got this bungee cord attached to our feet, and then we jump or fall or whatever we do here. And then at some other position down here, you're going to be upside down, and you're going to have this bungee cord attached to you. And so, and then maybe later it's fully stretched and you just are hitting the water. So this may be position A at the top, maybe B halfway down, and so maybe C right at the water. Okay, so at B, we're now moving. And so let's say we're moving and we've stored up maybe, I don't know, 40 joules in kinetic energy. Now we've lost some of this gravitational potential energy because we moved down. So maybe this is going to be 30. So we're quite far down there. And the bungee cord is warming up a little bit. So we've maybe lost some heat there, but not much. Say we lose 10 joules. Now we know the total is 120. It has to be 120 everywhere. So you can go down this column, 120, 120, 120. Now we go across the row and we see, these 4 things have to add to 120. Kinetic is 40, gravity is 30, heat's 10, that equals 80. This must be 40. And then that's how you figure out how much elastic energy is stored in the bungee cord. And then maybe when you get to the bottom, you've stopped because they make the cord just long enough so that you just stop without getting dumped. So you've stopped. You've also decided to make this 0, y equals 0 down here. So you've got no gravitational potential energy either because you're at the bottom. Now we've lost a little bit more with heat because this thing is stretched a little bit more. So let's say that's 20. Heat's always positive. I always put heat on the side that is positive. You don't have negative heat. Even though the work done by friction is a negative number, the heat is a positive number. Okay, we go across. What must we have as elastic energy? Well, if we've got lost 20 to heat, we've stopped, and we're at the bottom of our y equals 0 level, then this obviously is 100 joules, and that's how much energy has been stored in the bungee cord. So you can make this kind of table for any conservation of energy problem. It's very handy to do that. And if you make y equals 0 at the lowest point in the problem, then all your gravitational potential energies will be positive. Kinetic energy is always positive. Heat's always positive. Now, elastic potential energy, it's always positive as well. So all these numbers will be positive, and the total, this number has to be the same for every position. So that's a very handy way of doing conservation of energy problems. Okay, and the last equation on this formula sheet is that the force is negative du dx. Now where that comes from is that's a differential equation, which means this is a derivative. But if I want to make it an integral equation, I cross multiply and I go du is negative f dx. And you'll see here that when I integrate both sides, this becomes the change in potential energy. And this is the negative work done, which we already had, the very first equation we did here. So that is in fact exactly the same equation as this, that the change in potential energy from any kind of force. So this could be any force. If you put gravity there, you're going to get gravitational potential energy. If you put the elastic force, you're going to get elastic potential energy. So in general, change of potential energy is negative of the work done. Okay, so that concludes this chapter, these equations. You can now go to Mastering Physics. There's one more video to watch, and then you can do all the rest of the problems.